Welcome back to our deconstruction of the artificial mind. We've established that a modern neural network is a powerful, hierarchical system built from millions, often billions, of adjustable components called parameters or synaptic weights. This immediately presents a fundamental question. How can a network with millions of parameters possibly learn? A neural network is a collection of simple neurons, each making a small, weighted calculation. To learn, the entire system must adjust all its internal parameters to minimize its mistakes. The space of all possible combinations of weights is astronomically large. Without an efficient, targeted method, the task of finding the right combination would be computationally impossible, even for the most powerful supercomputers. Modern deep learning, the revolution that powers everything from ChatGPT to autonomous vehicles, is only feasible because of one brilliant, elegant, and computationally efficient algorithm. This algorithm takes a mistake and transforms it into a precise, actionable lesson for every single component. That brilliant algorithm is called backpropagation. It is the true engine of learning, and in this segment, we will deconstruct how it works. To appreciate the genius of backpropagation, let's first consider the impossible path, learning by random nudges. This is the simple, intuitive way we might wish a network could learn, but which is ultimately a computational dead end. The process would be a simple, brute force trial and error cycle. First, we would pick one of the millions of weights at random. Second, we would nudge it to increase or decrease its value by a small, random amount. Third, we would see if the network's overall error decreased after that change. Fourth, if the error decreased, we would keep the change as it was a good nudge. If the error increased, we would undo the change as it was a bad one. Finally, we would repeat this entire 5-step cycle for every single weight in the network, for every training sample, over and over again, potentially billions of times. As the diagram of the snail on the massive, tangled path suggests, this approach is not just slow, it's completely unrealistic. The time required for this brute force method to converge on a good solution, especially for a large network, would be astronomical, like waiting for the Andromeda galaxy to collide with our own. We need a targeted method that provides direction, not just luck. The random nudge approach is inherently inefficient because it's blind literally half the time. We are moving in the wrong direction, which increases the error and wastes computational resources. We don't need guesses, we need a compass. What we need is a way to know whether we should increase or decrease a weight's value to guarantee a reduction in the total network error. This certainty is the principle of gradient descent. To visualize this, imagine that the effect of a single weight on the total network error can be plotted as a curve, as shown in the diagram. Our current position on that curve is the black dot. Our goal is to descend to the bottom of the curve, the lowest point of error. The key insight is that the fastest way to walk downhill is always in the direction of the steepest slope. The gradient is simply the mathematical term for the slope of that error curve at the weight's current value. It is our compass. If the slope is pointing up a positive gradient, we must move the weight to the left to go downhill. If the slope is pointing down a negative gradient, we must move the weight to the right to go downhill. Backpropagation is the algorithm that efficiently calculates this gradient information for all millions of weights simultaneously, telling us the fastest way to descend to the minimum error. A network's learning process always begins with the call to adventure. A prediction goes wrong. First, an input sample travels through the network from left to right in a forward pass. Each layer performs its weighted sum and nonlinear activation, and the information flows until it reaches the output layer. The output layer then produces a set of scores, in this case, a probability distribution for 5 different classes. In our example, the true label for the input sample is class 3. However, the network's raw outputs assign the highest probability, 0.35, to class 1. The network therefore makes the incorrect prediction, class 1. This mistake generates a numerical difference between what the network predicted and what the true label was. This difference is the error. This error is more than just a bad score. It is the crucial starting point of the entire learning process. It is a powerful, quantitative signal that must now travel backward through the entire system to teach the network precisely what not to do. This error signal initiates the second and most critical phase of the entire learning cycle, the backward pass. The phase that follows is the journey back. how a mistake teaches the network. Backpropagation is the ingenious algorithm that turns the final, accumulated error into a precise lesson for every single component. As the diagram illustrates, the dark blue arrow represents the forward pass of the prediction, moving from left to right. The orange arrows represent the backward pass, learning, which takes the numerical information from the final error and travels backward through the network, from the last layer to the very first. This is not simply a reverse prediction. It is an efficient, targeted accounting process. The goal of this backward journey is to distribute a precise, quantitative message of responsibility to every single neuron and every single weight that contributed to the final output mistake. This message is critical because it tells each component its specific role in the error. It's the mechanism that ensures a neuron in the first layer, which may have only contributed a tiny, indirect amount to the final mistake, receives an appropriately tiny, indirect correction signal. This targeted delivery of the error gradient is the core function of backpropagation. The fundamental unit of information carried by the backpropagation algorithm is a number we call delta, represented by the Greek letter delta. Every neuron in the network, whether it's in the output layer or one of the deep hidden layers, must be assigned its own delta value during the backward pass. Delta quantifies the relationship between a neuron's output and the final network error. Essentially, it is a mathematical calculation that answers a critical question for that neuron. If this neuron's output changes by a small amount, how much does the final network error change, and in what direction? This allows the network to measure the sensitivity of the overall error to that specific neuron's action. It's a measure of blame or responsibility. If a neuron's output has a large impact on the final error, its delta will be large. If its output has almost no impact, its delta will be near zero. This delta value is the core of the learning signalets a personal, quantitative memo sent back to each neuron, telling it exactly how much it contributed to the final mistake. Without this precise measure, we would be back to the impossible path of random nudges. The backpropagation process must start at the most obvious place. The output layer. The journey begins at the source of the error. Here, calculating the deltas is the most straightforward because we can directly compare the network's output to the known truth, the target label. The target is typically formatted using one-hot encoding, where the correct class is 1 and all others are 0. Using a common error function, the delta for any output neuron is simply the difference between the desired result and the actual result. The calculation is straightforward. Delta for an output neuron equals target value minus neuron's output value. Let's look at the example in the diagram. Our target is the vector 1, 0, 0. For neuron C, the target is 1, but the neuron's actual output is a low 0.2. The delta for C, C delta, is 1 minus 0.2 equals 0.8. This positive 0.8 tells neuron C it was 0.8 units too low. Conversely, for neuron D, the target is 0, but its actual output is a high 0.8. The delta for D, D delta, is 0 minus 0.8 equals minus 0.8. This negative 0.8 tells neuron D it was 0.8 units too high. These two precise, quantified delta values are the first pieces of the error gradient information, and they are now ready to be propagated backward into the hidden layers. Now we address the most ingenious part of the algorithm, propagating the message to the hidden layers. How do we find the delta for a hidden neuron, like neuron A, which has no direct connection to the final error and therefore cannot be compared to a target label? The trick is to use the delta values we just calculated for the next layer. Neuron as output contributes to the input of all subsequent neurons, like C and D therefore, neuron as total responsibility for the final error its delta. A delta must be the sum of its downstream responsibilities. We are essentially combining the weighted error messages coming from the layer in front of us. To calculate a delta, we take the delta of each next layer neuron, C delta and D delta, and multiply it by the specific synaptic weight, connecting it back to a weights AC and AD. As the formula shows, a delta is calculated as the sum of AC multiplied by C delta and AD multiplied by D delta. The multiplication by the weight scales the downstream delta. If a weight is large, it means neuron as output had a greater influence on the error of the subsequent neuron, and thus A is assigned a greater portion of the responsibility. This process of weighted summation allows the error gradient to be accurately distributed through every single layer, from the output all the way back to the very first hidden layer. Comparing the two main phases of network operation reveals an elegant concept: a symmetrical flow of information. The entire backpropagation process is computationally brilliant because it mirrors the forward pass, calculating output in reverse. In the forward pass, you take inputs fo, go, multiply them by weights fh, gh, and sum them to get a neuron's output ho. The formula is ho equals fo multiplied by fh plus go multiplied by gh, and so on. In the backward pass, calculating delta, you take the deltas of the next layer, j delta, k delta, multiply them by the exact same connecting weights, hj, hk, and sum them to get the current neuron's delta, h delta. The formula is h delta equals hj multiplied by j delta plus hk multiplied by k delta, and so on. This symmetry means that the calculation required to determine the error gradient, the backward pass, is roughly as computationally efficient as the calculation required to make the initial prediction, the forward pass. If the forward pass takes 1 unit of time, the backward pass takes approximately the same 1 unit of time. This elegance and symmetry are the keys to practicality. This efficiency is what allows modern training software to parallelize the process across thousands of computing cores, making the training of vast, multi-billion parameter deep networks a feasible reality. Once every neuron has its precise delta-specific message of responsibility, the network is ready for the final step: the transformation, using deltas to update weights. Every single synaptic weight in the network is updated using a simple, proportional rule that combines 3 pieces of information. The first 2 we have already established. The output of the neuron, the weight is coming from the input neuron's output, AU, and the delta of the neuron, the weight is going to the output neuron's delta, C delta. The third piece of information, the learning rate, we will cover next. The core update rule is that the calculated change to a weight, AC, is directly proportional to the product of the first 2 values. The update rule is that the change to a weight is proportional to input neuron's output, multiplied by output neuron's delta. This product is the numerical representation of the gradient for that specific weight. If the input AU is large and the delta C delta is also large, their product is large, and the weight AC receives a significant correction. This change is then subtracted from the current weight, iteratively moving it toward the optimal value on the error curve. This process is repeated for every single weight in the entire network, completing one full cycle of learning. The third and final component in the weight update rule is arguably the most critical for successful training: the volume control, the learning rate, represented by the Greek letter eta. As we learned, the gradient tells us the exact direction of the steepest descent, but not how large a step to take. Taking steps that are too large can cause the network to constantly overshoot the optimal solution, potentially causing the weights to oscillate wildly and make the error worse. This results in the complete failure of the learning process. The learning rate, eta, is a crucial hyperparameter of value set by the human engineer that controls the size of these update steps. It's a small number, often 0.01 or 0.001, that scales the calculated weight change, acting as the volume control for the lesson. In the diagram, the product of AU and C delta is multiplied by eta to produce the final, controlled scaled chain. If the learning rate is set too high, the system overreacts, the training becomes unstable, and the network can never converge. If it is set too low, learning takes an incredibly long time. Finding the optimal learning rate is a delicate balance and is key to achieving rapid, stable learning in any deep neural network. Let's conclude our analysis by seeing backpropagation in action with the hero's trial, classifying the crescent moons. Our task is to train a simple classifier to find the boundary between 2 intertwined sets of data, points the blue and yellow crescent moons. This is a classic example of a nonlinearly separable problem, which we know the original perceptron could never solve. We need backpropagation to find a complex, curved decision boundary. The network we will use is a simple but deep architecture: 2 input neurons, 2 hidden layers with 4 neurons each, and one output neuron. This small network has a total of 37 synaptic weights that all need to be precisely adjusted. The goal is to use the backpropagation algorithm to adjust these 37 weights over many training steps, or epochs, so that the network's output correctly classifies every single point, achieving 100% accuracy. The success of this trial depends entirely on the efficient calculation and application of the error gradient. Our first attempt demonstrates a lesson in humility, the peril of a high learning rate. We begin training with a large learning rate, setting eta to 0.5. The result is a total failure, as evidenced by the three plots. The failed classification plot shows the network cannot find a useful boundary, essentially assigning all points to a single class. The center plot, no improvement, shows that the network's accuracy immediately stalls at 50% no better than random guessing and the loss remains high. The key insight comes from the right-hand plot, unstable weights. The lines representing the 37 weights are bouncing around erratically, constantly overshooting their goal, spiking to high positive and negative values. This is the consequence of a volume control set too high. The large learning rate causes the weight updates to be too massive, constantly throwing the system out of equilibrium. The network is correctly calculating the gradient, but it's taking such large steps that it can never settle into the optimal solution, preventing any real learning from taking place. Fortunately, the solution is simple, and it leads us onto the path to success, finding the right learning rate. By reducing the learning rate by a factor of 10, setting eta to a small, controlled value of 0.05, the network learns perfectly. The weight updates are now small, smooth, and controlled, allowing the network to gradually descend the error curve without overshooting. The perfect classification plot on the left shows the successful outcome. The network has found a complex, curved decision boundary that achieves 100% separation of the data. The rapid learning plot in the center shows the network's accuracy soaring to 1 and its loss dropping to near 0 in just 16 epochs of training. Finally, the stable weights plot on the right confirms the controlled learning process. The 37 weights are now moving in a smooth, coordinated, and highly stable manner, converging elegantly on a stable final configuration. This trial perfectly demonstrates that the power of deep learning lies not just in the complex architecture, but in the efficient, scaled application of the backpropagation algorithm. The journey of the error signal from prediction to the final weight update teaches us the true, profound meaning of the algorithm. The lesson learned: backpropagation propagates wisdom, not just error. It is not, as is often casually stated, merely propagating the error backward in a chaotic way. Instead, it is propagating the gradient of the error, the precise, actionable mathematical information that tells every single weight in the network exactly how much and in what direction it must change to improve. This is the wisdom, the most efficient path to reducing the mistake. This highly efficient, mathematically sound, and massively parallelizable algorithm is the reason modern deep learning is possible. It transforms every mistake into a specific lesson, allowing vast, multi-layered networks with billions of parameters to learn complex representations from experience. Backpropagation is the single, foundational engine that drives all the artificial intelligence successes we see in our modern world.